Hello, everybody. I hope you are doing well, and I hope you are learning your calculus really well at the same time. I know you have been taking calculus for a long time. This is your third semester after having passed 2 semesters of calculus 1 and 2, right? So now we are getting to the very end of that sequence of 3 calculus courses. And we now go to the last 2 sections and last 2 theorems of your undergraduate calculus sequence. All right, so this video deals with section 6.7 in our OpenStax book, and that is on Stokes theorem. After this, you have one more section, 6.8, on the divergence theorem, and that's it. Okay, so let's get started on Stokes theorem, which is an extension of Green's theorem. All right, 6.7. Stokes theorem. It is named after a mathematician named Stokes with an S at the end. And I subtitled this section, What if Green Could Fly? Okay, remember Green's theorem? Now, Green's theorem is on a two-dimensional region, which we called R, right? Remember, and I'll go over this again, but we had the region R on the XY plane, and there was a simple closed curve, which was the boundary of R. Right? It has to be closed, and it has to be simple closed curve. And we assume the orientation of counterclockwise, right, direction. And so we will review this. But let me review something else first, okay? So here, I'm going to go back to calculus 1 this time, by the way, because it really, when we talk about Stokes theorem, it really is an extension or a generalization or adding one dimension to Green's theorem, which I'm about to describe here. All right. So recall what the curl is, right? So if F is a three-dimensional vector space, which is P of XYZ, Q of XYZ, and R of XYZ, right? Remember what the curl was? Curl of F, which we can also denote as this gradient operator cross F, okay? And we denote it this way because this is the definition, ijk, and then partial x, partial y, partial z, p, q, r, right? And this, of course, turns out to be ry, and you can follow this along here, ry minus what? qz, right? And the next one will have the negative sign of rx minus pz, right? Or you can write this as pz minus rx because you just switch the order. And then the last one is qx minus py. And this last one should be familiar to you because this quix minus pay is what we had in Green's theorem, right? So let's go ahead. This was the ingredient, or I should say the integrand in Green's theorem. All right, and so we mentioned that if the vector field F has any kind of a circular motion or spin, right, then what happens is this curl is going to be coming out actually it should be in the other orientation. It should be going out like this, right? And so the curl of F would be the axis about which the circular or spinning motion of F is most prevalent. And that's how I described it. So that is the curl of F at every single point. It is a three-dimensional vector defined at every single point x, y, z, on which the vector field F is defined. So F itself is the vector field, right? But so is the curl of F. And again, it's showing the direction about which the rotation of F is the most common or the maximized. All right, and then the magnitude of this vector is represents the strength of that flow, so to speak. You don't really need to understand all the intricate interpretation of the curl of F at this point. All right, now if F is two-dimensional, P, Q, 0, okay, in R2, or I should say on R2, because that's the plane, then the curl of F is going to be ijk partial x, partial y, but remember there's no partial z, so that's going to be 0, pq 0 like this, and it just turns out to be 0, 0, qx minus quix minus pay. Okay, now imagine what's happening with this picture here, because what happens is if you look at so if you look at the picture that we drew in Green's theorem, then it's going to look like this. So this is the picture I had for Green's theorem, right? And what do we have? It's a region, and then of course the function f is defined. The vector field f, which is pq, is defined on every point on this region. All right, and so this is the picture. But if you look at this from a three-dimensional standpoint, which it is not, because Green's theorem only really deals with two-dimensional vectors field. But if you embed that on the xy plane, inside of, in R3, it's going to look like this. All right. Now, the picture is, you remember this RU cross RV, which is normal or perpendicular to to the tangent plane. If you look at this carefully, that's 0, 0. And then this happens to be the third component, right, of the three-dimensional vector field if you embed this into a three-dimensional space. And in this picture, it's just going to look like this, right? That's your 0, 0. And then, of course, that last one represents qx minus py, which is how long this vector is, right? So that's your n. Right. So this is what's happening. Now, let's go ahead and try to remember what Green's theorem says. And I know it could be sort of foggy and you may not get clear understanding of it, but that's okay. If you remember Green's theorem, the first version of it, the one that has to do with circulation or work about or around C, which is the boundary of this closed up region, this was equal to, remember what Green's theorem says? This is equal, this single integral or line integral about the curve C of the vector field f, okay, is equal to the double integral. Single integral is equal to the double integral. Okay, that is a strange part of this, maybe, but it is equal to quix minus pay, right, of dA. Right. This is what we said. Right? But if you just think about this, right? This is the same as, okay, this is the region. And if you think about what qx minus py is, it's really 0, 0, qx. You know what? I should move this over here. 1 second. This is supposed to be 0, 0, qx minus py, comma, 0, 0, 1, dA. Now, I know I wrote this in a very strange way. Usually it goes backward, right? If you try to solve this, you get, this, but that's okay. I am writing this in a longer way so that you can actually see what was really happening when we stated Green's theorem. You know what this is? This is the curl of f. And this is the normal vector. You see that? That's this vector here, okay? So it turns out what we were doing in Green's theorem is to say that this circulation or the work integral is equal to the double integral of curl of f dot n dA. Okay, so that's something to remember. And by the way, this you can think of this as your surface. Right? You can parametrize that surface even though it's on the xy plane. And so this would be the same as ds. Now this may look familiar. Okay, I hope it does. It is the, what is it? It's the flux, but it's not the flux of f, right? It's a flux of the curl of f. So what we will say in Stokes theorem is that the line integral, when you add one dimension to this, the line integral about the boundary of a surface, a parametrized surface, will be the flux, the integral of the flux of the curl of f. All right, so with that as with that said, let me define what Stokes theorem says. All right, and my subtitle or my sort of a quick introduction to that is, as I said before, what if Green's theorem or Green's person, okay, if Green could fly? So what if Green's theorem could fly? And what I mean by that is why don't we just give Green's theorem some wings, okay, and let it fly in space? And then what's going to happen? All right, Green is going to be on a magic carpet, and let me draw a magic carpet, and this will be a whole new world, of course, right? It's a dazzling point of view, and here is the magic carpet. Okay, so imagine a space. Okay, so it's R3, and then you have a parametrized surface. All right, I mean the surface is described right here, but it has a closed bound. Okay, in other words, it's bounded by this boundary curve C. Okay, so C is the boundary curve for this surface S, which of course, in order to describe the C, we have to parametrize it, right? So we use the parametrization we learned in the last section to describe this parametrized surface S, and whose boundary is C. And and this is the tricky part. I'll explain this later, but we orient this so that you know how you can find RU cross RV, which is your normal component N. Okay, so that would be your Rn cross RV, which is perpendicular to the tangent plane at this point to S. And using that as my orientation, we go counterclockwise, right? And so this direction of C is consistent with the counterclockwise orientation of this. Now, of course, in order for this to be possible, S has to be what is called an orientable surface or oriented surface, but we will not get into that, right? So in other words, if this is, again, let's say this is, like curved like a ball or something, this is still going up. The N is going from the bottom to the top part of S, and of course this has a lot to do with the flux and which direction and so on. But remember, if N is going up like this, then the orientation of the surface is going to be counterclockwise, going like this, which is consistent with this orientation of C, right? So with that orientation, Stokes' theorem says the following, right? The line integral, the work integral over the curve C of F dr. Okay, so in other words, this is the circulation or flow or the work done by F as you go along this of this curve C is equal to, very much like the Green's theorem, this is equal to what was on the right hand side? Well, we found out in the context of three-dimensional space, it's the curl of F dot N, and that's exactly what we have over in this side. It is the double integral. Okay, so this will be the surface integral over S of not F, but the curl of F dot N. Okay, and then ds. And of course, you know how to calculate this, right? Because last time we talked about what this thing is. Okay, it is, well, let's go ahead and write this. This is equal to the double integral of the, okay, let me go ahead and write down the short way of writing this. Remember what n ds was? This was, we call them ds with a bar. This is usually in the boldface in the book. Okay, but it really is, this is the way you calculate it. Remember, we don't use really ds for calculating anything or evaluating the double integral. And the way you do this is what? Yeah, if you remember, we use RU cross RV because that is your normal vector n, and then this ds has that denominator as a part of this, and they cancel each other, remember? And it turns out to be this, and then dA. And then at this point, I will have to fix s because we are no longer on the s plane or the space or the surface, but it's actually d, which is on the UV plane. So this dA is dV du or du dV, right? Okay, so this is how we are going to calculate this. But the important thing, what Stokes' theorem says, is that this line integral, be careful with this, the line integral, it's a one-dimensional line integral, of course, over this curve C, which is the boundary of S, turns out to be, okay, the double integral of the curl of F. It's a surface integral of the curl of F over this surface S. Now, the surface S could have a lots of different picture, right? So for instance, we will not be talking about sort of general S. Typical S would be something like this, all right? So this will be a upside down paraboloid. and the boundary will be this oriented curve at the bottom of this boundary, bottom of this paraboloid. Okay, and so this may be S. Okay, S could be just a plane. I mean, like maybe a disk, a flat disk that appears in this three-dimensional space. And in that case, the curve C will be the boundary circle, right? And so there are all kinds of different ways where you can apply this. And in fact, we will talk about maybe a box, okay? Imagine this is a box where this bottom is open and everything else is closed, okay? So it's a cube with the bottomless cube. Okay, every side, every one of these 6 sides is closed up. Maybe it's written, it's manufactured with a sheet metal or something, but the bottom is open, so it's a 5-sided cube. In that case, the boundary circle is going to be this bottom 4 edges, right? So that's a possibility. And in this case, the surface itself consists of 5 sides of the cube. So there are many different ways or the surfaces on which this Stokes theorem applies. Now, typically, we calculate, well, I can't say it typically. We calculate this by using the right-hand side, but sometimes we calculate the right-hand side by using the left-hand side. All right, so let me give you an example because that's the best way to illustrate a new mathematical concept, almost always. All right, so here is our first example. Let f be 2z x y square. Now, this is a vector field. It's a 3-dimensional vector field, okay? And the surface S is, and this is going to be one of these, right? Z is equal to 4 minus x squared minus y squared, and z is non-negative, okay? And so I am going to not ask to find right in the right-hand side in terms of the left or the left-hand side in terms of the right. The first example is to verify both sides of Stokes theorem are equal to each other. Okay, so in other words, I want you to find with this setting, this is a vector field F, and the surface S is this, and of course there's a naturally defined boundary curve of this surface. We will draw that in a minute, and then I want you to calculate this, and I want you to calculate this, and according to Stokes theorem, the answer will be the same. All right, so let's go ahead and imagine or visualize this thing first. If z is this, now you should be familiar with this, right? Because you can draw a picture of this. And if necessary, you can do I don't think it's necessary, but you can draw traces if you want to, right? So you know that when x and y are 0, z is 4. And if you do your traces, I mean, it's going to look like this. And it's an old familiar quadric surface, which we call the circular paraboloid, right? And because z is cut, or z is bounded by the xy plane here, or the surface is bounded by the xy plane, this is the curve, right? C is this circle on the xy plane of radius 2. How do I know it's radius 2? Because it's 4 minus x squared minus y squared, right? So think of this as your surface S. Okay, so the surface S is this paraboloid, and the boundary curve is this circle C on the xy plane. All right, now let's try to figure out. I'm going to set this up for you. What do we have to do for the right-hand side? It turns out the left-hand side is much easier, okay, because it's just you can parameterize the circle, and you can find f.dr as we did back in chapter or section 2. Right, so let's do the unfamiliar side, which is the right-hand side. You look at this, and you need the curl of f and ru and rv. So what is it that we need? Let's go ahead and find the curl of f. Okay, the curl of f is ijk partial x, partial y, partial z, 2z xy squared. And if you do this right, you get 2y minus 0, comma, and then z by itself, comma, and then you have, the partial of x with respect to x, that's 1, and that's it. Okay, so that's your curl. Now we are eventually going to have to write this in terms of u and v, because as you know, I mean, when you do this calculation, we don't use x, y, z. You just use u and v. Those are the two parameters. So speaking of parameters, you parameterize this s, and what do you get? Parameterize s. There are a couple of ways to parameterize a circular region, but remember, I mean, we're going to have to deal with this over the circular region. So it's better to use not the rectangular coordinate system, you know. Okay, let me explain what I'm talking about. This is one way to do this. Okay, because z is a function of x and y, you can do this, but then defining u and v and the bounds of u and v will be very difficult. So my suggestion is don't do this, okay? You notice here, everything is circular. We are going to be integrating over the circle. So let's go ahead and try to parameterize it this way. R of u v is equal to, now remember, it has to, take care of the whole thing here, right? So u cosine v, u sine v. This will help you, and I know it's not easy and it's not trivial to come up with a parameterization of a given surface, but let's look at this. Because you have the circular, let's see, circular contour and level curves. Okay, it's probably good, and of course the radius keeps changing as you go up and down here. So it's good to have x is equal to u cosine v and y equal to u sine v. And let's see what happens, because I would like to know what x squared plus y squared is. Eventually, I have to show that z is 4 minus x squared minus y squared. All right, so this will be u squared cosine square v plus u square sine square v. And that's, of course, u squared. Okay, and so if I want z to be 4 minus x squared plus y squared in the parentheses, I just put them in the parentheses, that's going to be 4 minus u squared, right? And that's exactly what I need to have for my z component, 4 minus u squared. I hope you can see that. All right, then we have this parameterization, and u goes from what? Well, look, u goes from 0, and at this, it's a radius, right? It's a radius of this circle, and so 0 to 2. And then v, of course, goes from 0 to 2 pi. Okay, and when z is, when u is 0, then you have, of course, 4 minus 0, which is 4, right? And that's, of course, this top point. And if u is, did I say that? If u is 0, that's 4. The radius, height is 4. If u is 2, then you have 4 minus 4. And so the radius is going to be 2, but the z component is 0, and that's this circle on the xy plane. So this is fine. And now, of course, I have to find Ru cross Rv. So let's go ahead and calculate Ru, which is cosine v sine v negative 2u. Okay, and Rv is a negative u sine v u cosine v 0, remember, because this has no v in it. And then, of course, I need to have Ru cross Rv, which is, what do you get when you take the cross product of these? Okay, you got 0 minus negative, so it's positive 2u squared cosine v. That's the first part. The next part will be 2u squared sine v. Right, that's this, and then minus 0, of course, right? And then the last one is a little tricky. I don't know if I want to write everything, but if you look at it, it's going to be u cosine square minus negative u sine square, or it's u cosine square plus u sine square. Well, that's just u, right? Okay, so this is what you get on this side, or on the part that's required. All right, now let's go back to the curl of f. All right, remember, you may, when you start to do these problems, at least for the first few, you may want to write down this equation, okay, especially the right-hand side, which is the one you are not familiar with, because this will remind you all the things you need, all the ingredients you need to put into this big stew of this surface integral, right? We have a curl of f. Well, we don't quite have curl of f in terms of u and v yet, but we've just calculated this. So we will be set to integrate, ready to integrate this as soon as we find the curl of f and write that in the u and v terms. Remember, curl of f is 2i z1. Okay. What is y in my parametrization? That's u sine v, and z is 4 minus u squared, and the last one is 1, right? And this is a nice way to write this. And then I wish, I wish I could move this. Wow, you can move that. You know why I'm doing this, right? Because I would like to align these two. It would be really nice to have a sort of a one-to-one match between these. And I'm not going to write this, but because I need to do what? Okay, I need to add. I need to find the dot product of this, and so therefore the curl of f dotted ru cross rv is equal to, what is that? It looks like it's 2u cubed sine v cosine v. Now remember, this is not a vector anymore, so I'm going to say plus, and the middle one is kind of messy, isn't it? Let's see what we can come up with. It's actually, yeah, hold on a second, and let's see what's going on here. Okay, just going back one step backwards here. Y was u sine v, so I have 2y here, which means I have to have 2 of these. So it's 2u sine v, and then you have the middle one. What's the middle one here? This is, hold on a second. Okay, so let me go back here too. This is not a major error here, but when I calculated the curl, I think I misspelled this. So the middle term here, it will be negative of this minus that, right? So it'll be negative of 0 minus, and then when I took the partial of 2z with respect to z, I wrote down z, but it should be 2, okay? So I apologize for that. It's really number 2. And so it's not 4 minus u squared. I knew that this was going to be very complicated. I thought something was wrong. So let me go ahead and fix that. This should be just a number 2 because that's what it was. So that's 2. And this is also 2. Okay. 2 and z look very similar to each other. I would strongly encourage you to cross your z, like most European people do. Because some of you write 2 this way and some of you write z this way, and it's very hard to distinguish these. Okay, so going back here, I have 2u squared cosine and then 2u sine, so this will be 4u cubed sine v cosine v. Next one will be 4u squared sine v, and then plus u. Okay, so that is my integrand. Finally, I have this integrand. All right, so let's go ahead and figure out what the right-hand side is. The double integral over s of the curl of f dot n ds. Remember, this is the flux of the curl of f, not the flux of f, but the flux of the curl of f over the surface s. And that we know is the double integral over the region d, which is defined by u and v, of this thing here, curl of f dot ru cross rv. Now, you don't have to write this part down, obviously, right? But I want to remind myself that is what I'm calculating. Now, let's go to our u and v here, because my v was from 0 to 2 pi. My u is from 0 to 2, right? And then the curl of f dot, this whole thing is what I calculated. It's 4u cubed sine v cosine v plus 4u squared sine v plus u, all of this dv du. Okay, so can we actually, which one was v? V was the one that goes from 2 pi, so this should be switched, du dv, because u goes from 0 to 2. All right. it looks, complicated, and it is a complicated expression, especially for our first example. But I want you to see that oftentimes one side is much more complicated, right? Now, after, in just a few seconds, we'll go to the left-hand side, which you will appreciate because it'll be much easier, all right? So, but let's go back and try to finish this. This is what? It's u to the fourth. Remember, the first integration is with respect to u. So it's 4 u to the fourth sine v cosine v plus this will become 4/3 u cubed sine v, and then plus 1/2 u square, and then we go from 0 to 2 and we integrate this part first, okay? And let's go ahead and simplify that. When you put 2 to the fourth, that's 16 sine v cosine v plus, and this is going to be a big number, 8 times 4 is 32 over 3 sine v plus, and then you plug in 4, that's 2. And so this is our new integrand with respect to v. All right, so now you're going to have to figure out some little tricky things here. First, you know what, because I have the sign, and this will happen as you do your homework too. You may want to go back and look up these things here. Sine v, cosine v. All right, do you remember how to do that one? Yeah, you can do u substitution. U is equal to sine v, then du is cosine v, dv, which is what you have here. So this will be equal to u du, very simple. By the way, this u is not the same u as over here. And this is 1/2 u square plus c, which is 1/2 sine square plus c, right? And so at this point, I'm going to go ahead and do this. This is going to be 8 sine square v. And okay, plus 32 over 3. And then what's the antiderivative of sine? That's negative cosine of v, right? And then you have 2v. Now we go from 0 to 2 pi. Right? And notice here, despite all the hard work, you really didn't have to do all the work because, I mean, what's the sine of 2 pi squared? Well, that's 0 squared. That's 0, right? And then sine of 0 squared is also 0. So this will just be 0, okay? And yeah, so that will give you a 0. And the cosine, oh, that's different. But remember, cosine of 2 pi is 1, and cosine of 0 is also 1. So there is no difference because these are just periodic functions of 2 pi. All right, and then the last one, 2v, this will be 2 times 2 pi minus 0. And so the answer is going to be 4 pi. All right, what did we just calculate? Remember, we just calculated the harder side of this because the question was to verify that both sides of Stokes theorem are equal to each other. And we just said the right-hand side is equal to, remember the right-hand side, is equal to 4 pi. Okay, now it's your turn. Let's go to the left-hand side. Okay, now what do you have to do for the left-hand side? Well, remember, this was my C, right? So C is a curve, which is a radius 2. It's a circle of radius 2 on the xy plane. All right, and you are given f. All right, so what I want you to do is I'm going to give you a moment, and I want you to work on this line integral over C of the vector field f. Okay, so what we are trying to find then is the C of f dr. You know how to do that, all right? So I want you to go ahead and work on this. And when you get 4 pi, which you should, then you can come back and start the next part of this video. All right, let's go ahead and do that.